Huh? You can't see. Oh. We stated that forces acting on an object can do work. And in this example, there were, 4 forces that acted on this object. Did all of these forces contribute to the work done on the object?
No.
No. We recognize right away that even if this object were to move some distance across the floor, that not all of these forces actually are doing work. We know that the normal force doesn't do work because the normal force is perpendicular to the displacement. Remember, work had 3 buckets. There's the force, there's the displacement, and then there's the cosine of the angle between them. The normal force does not contribute to the displacement. It is perpendicular to the displacement, and therefore it does no work. Now, that also suggests then that the weight doesn't do any work either. Now remember, just because these forces don't contribute to the work doesn't mean they don't contribute to what's happening. We know the weight and the normal force are related to the frictional force. So we know that they are related to forces that do work. They themselves, though, are not doing work. Yes, sir? All right. Now, it is true that the applied force does work, but does all of the applied force do work? No, just the part of that force that's in the direction of motion does work. I'm going to say that again because I want to make sure you fully appreciate. It's only the portion of a force that is directed in the direction of motion that does any of the work. Now, that being said, the frictional force, does it do work? Yes. It's not directed in the direction it moves, but it's directed against the direction it moves. So it did negative work. In fact, if we remember, the angle between the displacement and the friction was 180 degrees, forcing a cosine of 180, which is -1, which means positive work are forces that are contributing to increasing the kinetic energy of the object. Well, negative work is contributing to decreasing the energy of the object. Again, positive work is increasing the energy of the object. Negative work is decreasing the energy of the object. Bringing us to the work-energy theorem. The work-energy theorem states that the net work equals the change in kinetic energy. The net work equals the change in the kinetic energy. This could be phrased work done by an unbalanced force. Can change the kinetic energy of the object. Right, there had to be an unbalanced force for the object to accelerate. So we know there's only going to be a change in kinetic energy if there's an acceleration. Kinetic energy we defined as 1/2 mv squared. Now, this is what we culminated with on Friday. Are there any questions about this? You guys are a pretty smart group. I want you to pay very close attention to what I'm about to do, okay? How many of you remember this? Thank you. How many of you remember this? All right, you recognize this as one of your motion equations? Okay. The motion equations aren't exactly what you think they are, although I showed you where they came from, and we derived all of them in class based on, well, basically the area and the slope of a graph. Remember? They contain a lot more information than you might think. I want you to look closely at what I'm about to do here. I'm going to do a little algebra. The first thing I'm going to do is I'm going to divide both sides by 2. Okay? I'm going to multiply both sides by m, the mass of an object. Now, the left side, I'm going to group. Now, do you see what the left side is? What would we associate with MA?
Forces.
Right, it represents the net force, doesn't it? If there's an unbalanced force, it will be equal to MA. Delta X is just displacement. Now, look at the right side. If I distribute the 1/2 and the m, I will get 1/2 mv final squared minus 1/2 mv initial squared. You do recognize that as the change in kinetic energy, right? And if you're not seeing this, then let me bring it together for you. The whole time we've been here doing motion equation work, it's actually been the work energy theorem the whole time. You see, all these things are linked together. So this motion equation is the work energy theorem. It states that if you have an acceleration over some distance, it's going to change the object's velocity. It also means that any change in velocity means that work was done. Now, that's a bit of a lie. Yes, sir?
Where'd you get the m from to multiply it on both sides?
Well, the object probably has mass, so I just picked out an m and said that's its mass. Now, a bit of a lie. And I want you to pay attention to why it's a bit of a lie. Because you guys are complacent sometimes, and right now is one of those times where I think you might be complacent. I want you to imagine if I had a ball on a string and I was swinging it around my head. You can imagine that, right? Having done this in class? There's going to be this one moment where the string is here and the ball has a velocity in that direction. Does that make sense? The ball is being acted on by the string, which is pulling this way with tension like that. A few moments later, the ball will be over here with a velocity like that. The string will have moved now, so the string is over here, and there will be a tension in the string like that. This is an unbalanced force. This unbalanced force would be equal to MAC. Correct? What force is causing circular motion? What is the unbalanced force? The tension. That is the force that is perpendicular to the velocity. So it has to be the one that is causing centripetal acceleration. This system has an unbalanced force. Does the tension do work on the ball?
Yes.
I am intentionally trying to trick you. I want you to think it through all the way. Let me ask this. If the ball's velocity is 10 meters per second here, based on what we've talked about, what would its velocity be here?
Maybe 10.
10 meters per second, sure. Its direction has changed, but its speed hasn't. what would its change in kinetic energy be then?
There's no change.
How many of you agree there's no change? Yeah. Has any work been done on the ball? By definition, no. There's been no net work done on the ball because the ball's kinetic energy didn't change. You see, it's not really about velocity. In this case, it's about speed. Net work changes the speed of an object. In this case, the tension is acting on the ball. The tension is unbalanced. But by definition, the tension can't do work because this is 90 degrees. And what is the cosine of 90 degrees? The tension can't do work because it's perpendicular to the displacement. This tension is an unbalanced force. That unbalanced force changes the direction of the ball, but it doesn't do work on the system. Thus, the kinetic energy remains constant. So it's not just about an unbalanced force. There has to be a part of the force in the direction of motion. That is such a critical attribute. But the best way to understand it is that if the speed doesn't change, no work was done. It has to get faster or get slower. Remember, the most basic form of energy is kinetic energy. You have to change that. And energy does not have direction. It's a scalar quantity. The fact that it's squared is what strips away any of the directional part. Remember, if it's positive, it stays positive. If it's negative, it becomes positive. Anything about direction is stripped away when we square it. So, work is only done if there's a component of the force in the direction or against the direction of motion. This is an easy place to trick you. You won't be tricked now. Centripetal motion is a special case where there's no work done, even though there's an unbalanced force. All right. This point forward is new. Everything else is what we talked about Friday. This is actually brand new. I'm going to use Friday's example, though, for it. In Friday's example, we talked about bench pressing. Do you guys remember that? How was your workout on Friday?
Pretty good.
Excellent. It was legs and abs, right? Yeah, not my favorite. I'll be honest, I didn't do a workout on Friday. I was supposed to, but I decided it was Friday, and I would rather not. But I was happy. I ran the voice of Shelton, yeah.
Yeah, you just like telepathy, right?
All right, so I want you to imagine I have this box, mass M, resting on the ground. I'm going to do work lifting the box. So you guys are already aware that if I lift the box at constant velocity, I would have to apply a force up equivalent to the weight of the box. Right? This would be the applied force on the box by me to lift it. It would have to equal mg. The work I would do in lifting it would be mg times, well, let's say I lift the box a distance h, some height above the ground. So the displacement would be h, and will we all agree that my applied force is in the direction the box moves? Is that okay with all of you? I pushed up on the box went up, so the angle between my upward force and up is 0. So this would be the cosine of 0 degrees. We okay with that? That's the work done by the applied force. How much work was done by gravity? Same amount, but negative. So gravity did negative mgh worth of work, so that the change in kinetic energy of the box was 0. Everybody all good on that? Still Friday. So let's accelerate to today. Box is now up here. I have successfully moved the box. Once the box is there anything really different about the box? It's higher than it was, but there's nothing different about the box. Now, if I were to drop the box, would you all agree that gravity would do positive work on the box? Now, let's be careful here. Will the force be balanced or unbalanced if I drop the box? Unbalanced. Would you all agree that the amount of work done by gravity would equal mgh? Would you all agree that the work done by gravity would be equal to mgh? That the force on the box would be mg, it would be downwards, and it would be pulled downwards, so the displacement would be downwards. Cosine 0 degrees this time on the way downwards. So I would have mgh worth of work done by gravity pulling the box back to the ground. Everybody follow that okay? If there's no other force acting on the box, this would have to equal the change in kinetic energy of the box. Work energy theorem. Somebody realized that this would happen. In fact, realized that under conditions like this, where conservative forces are acting on objects, there seems to be this exchange, an exchange of energy, switching between one type and another. Think of this for a moment. What if I had, let's see, a table with a kind of wall at the edge of it, and I attach a spring to it. If I place a box on the table, say right here, it's not like the box is going to spontaneously shoot off to the right. But if I take the box and pull it back against the spring and let it go, would you all agree the box is going to shoot off to the right? No doubt in your mind? Now, would you agree that as I pull the box against the spring, I have to do work on the spring? Because I am pushing on the box in this direction. The box is going in that direction. I do positive work on the box. Does that make sense? What direction is the spring pushing on the box? And the spring is pushing this way on the box, but the box is going this way. So while I'm doing positive work on the box, the spring is doing negative work on the box. But if I let go, all of a sudden the spring can do positive work on the box, and that work would be transformed into kinetic energy. Somebody has picked up on this idea that we can exchange different types of energy. In fact, take this one step further. Could you imagine a case where I take the same spring, place it on the ground, take my box, pull it back against the spring. I've done work against the spring. The spring has done work against the box. And then I let it go. The spring does work against the box and shoots the box upwards into the air, where now gravity has stopped the box and is going to bring it back down, where it's going to hit the spring and shoot back up, come back down, shoot back up, come back down, and you get it, right? This would go on forever. Now, if you're really paying attention, and I hope that you are, there's this constant interplay between the work done by the spring, the kinetic energy of the box, and the work done by gravity. Are you seeing that? Well, we're not the only ones to see this. This idea that you can do work against a force that you could save for later has a name. It's called potential energy. And I know you guys all know about this because you've all had physical science. So I know that you were taught information about potential energy. I'll state a few things about potential energy that are the same as what you know. Potential energy is stored energy. And I know you've heard that before. In fact, potential energy is often called the energy of position, because the storage of the energy is often based on the position of the object. How high you lifted it, how far you pulled it back against the spring, its position. However, potential energy isn't exactly what you learned in middle school. There are some differences, some things that you need to understand are of importance. First, potential energy only exists if you can do work against a conservative force. That's really what potential energy is. Potential energy is stored when you do work against a conservative force. Gravity is a conservative force. The spring is a conservative force. Next, potential energy is an interaction. It's not holistic. There's no energy stored in the box. There's energy stored in the interaction between the box and the spring. Or the energy is stored in the interaction between the box and the earth. So the energy isn't stored in the box. There's nothing about the box that's any different when you push it against the spring or lift it above the ground. But there is something different about the interaction between the box and that object, the spring or the earth. That's where the energy is actually stored. We're going to treat potential energy the same way we treat kinetic energy, as part of a system. And we're going to use uppercase U for potential energy. Gravitational potential energy is going to be exactly what you think it's going to be. It's going to be equal to mgh. I'm going to write h a little different than I did before. I'm going to write it as a difference. Now, the reason I'm writing it this way is because potential energy, in all of its forms, including the one we're describing right now, is based on the work you do in changing the position of the object. So imagine I have a table right here, and I place my object on the table. All right. If I lift the box upwards off the table, we all know that I've done work on the box against gravity, and that work would be related to how high I lifted the box off the table. Does that make sense? Now, if I sit here and hold the box this high off the table, I could hold it there indefinitely. But no matter when I let it go, would you all agree it will fall to the table and reach the table traveling at the same speed, whether I let it go today or next year? That as long as I keep it this same height, I will get back the work I put into it whenever I release it. You guys all agree with that? That's why we say that the energy is stored, because we can get it back whenever we want. It's like taking a bunch of water balloons up to the second story of your house and sitting outside your window and waiting for people to walk by and dropping them on those people. You can have the water balloons there for years. Right when you need them, you would have them at the ready. You would have done work taking them up the stairs, a little at a time, so you had a good stockpile of water balloons. So then, whenever necessary, you could drop them. Will the energy of the water balloons change? Nope. Once they're there, they're ready to be used. Look, Now, here's an important difference, and it's something I want to make sure you really are paying attention to, which is why there's this little H naught here. If I lift the box up and then slide the table out from underneath the box, has something about the box changed? No. But what has changed? Its height is now different, right? Now, the box doesn't suddenly have more energy. There's nothing different about the box. But the potential for the box to fall a larger distance has increased. Wouldn't you say? The box could fall much further than before. And so for all intents and purposes, the box has more energy. If you drop it now, it will be going faster when it reaches the ground than when it reaches the table. Potential energy isn't a holistic quantity like kinetic energy is. If it's moving, it has that amount of energy. Potential energy is a relative concept, especially gravitational potential energy. It is relative to a reference level. In order to know how much potential energy an object has, you need to know potentially its lowest place it can attain. I'll say that again so you have it in your notes that way. But to understand how much potential energy something has, you need to know what the reference level is. The reference level represents the lowest position the object could possibly attain. Now look, we know this. We know this intuitively. None of you jump to the second story of the building. All of you take the stairs. Because the stairs is a series of short hops where you can do small amounts of work a little at a time, lifting you up a little bit at a time. Little bits of potential energy added all together till eventually you got to the second floor. Otherwise, you would have to do all the work at once to get to the second floor. And trust me, that means most of you would never make it to the second floor. Not if you had to do all the work at once, jump to the second floor. So we let you do little hops, little amounts of potential energy, something that you can manage. The box had been given the potential energy to reach the table already. It already had that energy relative to the floor of the room. You lifting it added energy to the box, but it already had energy relative to the floor. So nothing about the box had changed. You had increased its potential, You had increased its potential energy when you lifted it off the table, but somebody else gave the box potential energy when they put it on the table. Somebody else brought it upstairs to get it in the frickin' room. So nothing about the box is different. When we talk about potential energy, though, we are talking about the lowest level it could attain. I mean, I want you to imagine, you guys leave your water bottles in here all the time, but the water bottles are almost always getting knocked off the tables. Almost always. There's always some time where the water bottles get knocked off the table, and we all look at that person like you're an idiot, especially those big Visco Girl bottles that clang like crazy when they finally hit the ground. Love those bottles. So I placed my water bottle squarely in the middle of the table. Why? Because there's no chance it can fall off from the middle. But if I place it there, now it could fall off. Has the potential energy of the bottle changed? No. But the potential for it to fall has greatly increased, wouldn't you say? And I don't use that word haphazardly. Potential energy is like that. What is the potential of the object to do? Right now, I'd say there's a good chance it could fall off. I'd rate that potential energy pretty high. Let's say it probably has, based on the height of the table, which is, by the way, 0.76 centimeters. I'm sorry, it's 76 centimeters, 0.76 meters. I'd say that let's say 100-gram water bottle does have potential energy. How much potential energy? Well, I'm thinking it's got 0.1 times 10 times 0.76. Or last time I checked, 7.6 joules of energy. We good so far? How fast would it be going if it fell off the table? Could you figure it out? Do you have a question or an answer?
How is it 7.6 if it's 0.1 times 10, which would be 1, and then times 0.76?
Because I can't add? Well, actually, in this case, multiply.
It would be 0.76.
Right. I get it. And I appreciate the correction. Now, back to my question. Could you figure out how fast it's going when it reaches the ground? I think Matt could. I would like the rest of you to, though. Think about it this way. If it falls off the table, will gravity do work on the bottle? Do you know how much work gravity will do on the bottle? Will that be an unbalanced force acting on the bottle? Which would suggest that there would be a change in the kinetic energy of the bottle. Since the bottle currently has no kinetic energy, that change in kinetic energy would quite literally be all of the energy the bottle had before. You should be able to figure out how fast the bottle strikes the ground. No motion equation, just comparing the energy. All right.